Hey everybody. So now let's find the internal forces and moments of this beam subject to a distributed load. So something like this, you have to be very careful. So let's go through this. So step 1, draw the free body diagram. All right, so here's a beam. Here's our coordinate system already, XY. So there's a pin at A, which I will decompose. Okay, there's a roller at C. And then there's this distributed load. Now, you can represent a distributed load as a single discrete force, right? The magnitude of that force is the area of the shape, right? So that's a triangle. That is 6 meters over here. So 1/2 base times height. Okay, so that's 180 newtons. And the location of that force is at the centroid of the shape. So since it's a triangle, it's 2/3 of the way over this way. So 2/3 of 6 meters. All right, so here to here is 4 meters. Here to here is 8 meters. Okay, so this is this. And now let's solve for the reactions at the supports. Okay, so in the x direction, we got AX and nothing else. In the y direction, AY plus C minus 180 equals 0. And then let's sum torque about anywhere we want. How about over here? Okay, so there's torque from C, so that's 12 meters times C minus 4 meters times 180 newtons. Okay, so C is, let's see, 4 times 180 over 12. So 180 over 3 is 60. Okay, so 60 newtons. And then we can plug that value in right there. So AY is 180 minus C. So that's 120. And AX is 0. Okay, so we got all 3 reactions. So if I draw, so let me just show you something. AX is 0, AY is 120, C is 60, and then I had the 180 Newton force like this. Okay, and then point B is right here. Okay, so now it's time to cut through this section at B, right? Okay, now let's be very careful. This was okay when we were analyzing the reactions at the supports. But now that it's time to section it through that point, this is okay to cut it like this. This is not okay to cut it like this. Okay, so this is very important. This representation was only to solve for the reactions at the supports. It is not okay to cut a section like that with this representation. That is not okay. You're not going to get the right answers. You have to go back. So this is not okay. Right. This, you have to go back to the original representation with the distributed load. Then you can cut a section like that. That is the correct way to do it. Okay, so let's do that. Let me just copy this over here. Okay, so we had our beam, and then now we know this was, what were they? 120 and 60. Okay, now we have our distributed load like this. Okay, now we can cut through point C like this. This is 3 meters, right? That is okay. This is point B. So what happens when you cut it like that? I'll just draw where I have more space over here. Okay, so there's the left section. Here's the right section. And we cut right through the distributed load. Right, like this. There's the support here. There's a support over here. And so here to here is 3 meters. Here to here is 6 meters. And here to here is 9 meters, right? And here to here is 60 newtons per meter. How high is this? How high is this? So we know the slope is, what is a slope? Rise over run. So it's 10 newtons. Let me just write it like this. 60 over 6, right? That's the slope. So this is 3 meters. So this has got to be 30, right? Over here. Okay, so that's what happens when we cut right through the distributed load, right? We cut right through the distributed load. And now what's happening over here? Internal. There's axial force. This way, right? Shear, which is the shear, this way. And bending moment, this way. This way. Okay, so now if we want to solve for axial force, shear, and bending moment, you can either take this free body diagram, analyze it, or this one. Either way, you're going to get the same answer, so it's up to you. I feel like this one is a little bit simpler. So now that we have the free body diagram like this, now it's okay to represent this distributed load as a single force. So what would that single force be? The area of the shape, so it's a triangle, 1/2 base times height, right? So 45 newtons. And then the location of that single discrete force is at the centroid of the shape, which is right here. So this is 3 meters, so this is 2/3 of the way over. So here to here is 2 meters, right? Here to here is 1 meter. Okay, and then let me fill in the rest of it. Okay, so now some forces X, Y, torque about somewhere clever. So in the X direction, we got P. Is that it? Yep, that's it. Okay, Y direction, 120 newtons, minus 45, minus V. Is that everything? Okay. Okay, let's sum torque about anywhere we want. So I'm going to sum torque about this side. Okay, so the torque from this would be negative 3 meters times 120. Then the torque from that 45 Newton is plus 1 meter, 45 Newtons. And there's no torque from this or this about over here. And then let's not forget that couple, the bending moment, which is in the positive z direction. Okay, so let's solve for our three unknowns. P is 0. V is 120 minus 45. So that's 75. And then M is negative all this. So whatever, 360 minus 45. So that is 315. Okay. Now, okay, so that's, I should write my units over here. Newton meters. Okay. So you could have, if you wanted to, analyzed this section. It looks more complicated, so personally, I wouldn't. I would go with this. This section looked easier to analyze, right? This one. But, I mean, you could totally analyze this one. So just as an exercise, let's say I did that. So some forces in X. Okay, we got minus P. That's it. Some forces in Y. Okay. Again, we can represent this distributed load as a single discrete force. And then the magnitude would be, let's see, I'm just going to decompose it because it looks like a rectangle with a triangle on top of it. So the rectangle is 30 by, here to here's 3, right? 3, so that's 90. So just for the rectangle alone, it's 90. At the centroid of the rectangle, which is over here. So here to here would be 1.5 meters. Right? And then this is the leftovers, 9 minus 1.5. So that would be 6.5. Oh no, 7.5. Okay, and then for the triangle part, 1/2 base times height, 1/2 base times height. So this is 30, right? The rectangle is 30. Right here to here is 30. Here to here is 30. Okay, so the triangle part would be 45. And then at the centroid of the triangle, which is 2/3 of the way over, so here to here would be 2 meters. Okay, and then all the rest of it, V, bending moment. Okay, so some forces X, some forces Y, we got V minus 90 minus 45 plus 60. Okay, did we get everything? I think so. Okay. Some torque about, where should we sum torque? How about over here? So I'm going to sum torque about the left end of that section of the beam. So there's torque from this. So how far is that? 9 meters. So 9 times 60. And then there's torque from this, which is 1.5 meters times 90. There's torque from this, 2 meters times 45. And let's not forget the couple from the bending moment, which is in the negative direction. Okay, I think I got everything. All right, so P is 0. V is, let's see, 135 minus 60 is 75. Okay, and then M is, okay, so that's 90 plus 135 minus 540. Oh no, I got the minus. This goes on that side. So minus 90 minus 135 plus 540. Okay, so I don't know, I'm gonna calculator. Okay, so calculator, that's 315. Okay, hopefully that's the same answers we got earlier. Okay, so, right, same. Okay, so same answer either way. And I felt like this way was a little bit easier than this section. Okay, so again, be very careful when you cut the section, not like this, right? Not like this. Not okay. Just be careful. All right, so keep on practicing. I'll see you in the next video.